whatever we are going to solve, problems on geometrical optics. In the next class we will be discussing all different kinds of problem you require to revise geometrical optics, starting from refraction of light. Today let us start refraction with this topic, refraction through rectangular glass slab. What is a rectangular glass slab? Rectangular glass slab is of three-dimensional shape. I am just taking a cross section of it. Imagine this is a rectangular glass slab. Light allowed to fall on it. It has, say, refractive index mu and thickness is equal to T. When light is incident on it, it will suffer refraction. This is your rectangular glass slab. Light entering. At this point of incidence, this is the normal, light get refracted. Then at this point again refraction, isn't it? Then finally it will be refracted. This manner. So inside the glass slab, light suffer refraction. Thickness of the slab we have taken T and diffractive index mu. Angle of incidence be I1. Here when incident at O1, at the point O1, the angle of refraction be R1. So this has to be R1 because both are normal and these two sides are parallel. If this is a rectangular glass slab, then these two sides are parallel and these two sides also. I have taken the cross section. So if this one R1, this is going to be R1 and this angle of emergence be I2. Okay. First we are going to prove that I1 equal to I2. That angle of incidence equal to angle of emergence. This medium is air. Surrounding medium is air only. Air, vacuum, whatever you say. So if I consider absolute refractive index of this medium, glass or any refracting surface is mu, then considering a refraction at O1, we go by generalized Snell's law. Air has refractive index 1. Last class we have seen that sin I by sin R equal to mu2 by mu1. Mu2 is the refractive index of second medium, mu1 is the refractive index of first medium. So mu1 into sin I will be equal to mu2 into sin R. This is called generalized Snell's law. The angle, sine of the angle in the medium into refractive index of the medium, sine of the angle in the second medium into refractive index of that medium. So considering a refraction at O1, what can we write? 1 into sin I1 will be equal to mu into sin R1. This is number 1. Now consider this refracted ray again refracted here at the point O2. This point is O2. Refraction at O2. What do you observe? This has refractive index mu. This mu into sin R1 equal to 1 into sin I2. Clear? This you understand? By generalized Snell's law we get this thing. Now let us multiply these two equations. Multiplying 1 by 2. Multiplying 1 by 2. What do I get? If you multiply 1 by 2, then 1 into sin I1 mu into sin R1, that is mu into sin R1, 1 into sin I2. If you cancel the factor mu sin R1, this implies sin I1 sin I2. So I1 equal to I2. Clear? So angle of incidence going to be equal to angle of emergence. This I1 equal to I2, angle of incidence, angle of emergence. So don't you say that if this is the incident ray and O2b is the refracted ray, final emergent ray, then they are parallel to each other. Don't you say that? They are really parallel here. A1 and O2b, they are parallel because you have got I1 equal to I2. Then what happens to this light ray? Which light ray? That is light ray if you produce it forward, and this one if you produce in backward. Don't you think that these two rays are parallel to each other? Because this I1 will be here also. That is equal to I2. So this ray and this ray has to be parallel to each other. Clear? So what happened to that light ray? Light ray had changed the path. Okay? That is called lateral shift. So you have got a lateral shift over there. Light ray refracted, but very interesting to note that light ray suffer lateral shift. It was going in one direction. Now finally it will emerge in such a manner that this ray will be parallel to this final emergent ray. These two are parallel. Okay, so we'll say that if this is the produced part here, this is the produced part here backward, then O1m, if you draw a perpendicular, this O1m going to be O1m going to be the lateral shift. Okay, your problem is to find the value of this lateral shift when light ray suffer a refraction through a rectangular glass slab. Rectangular glass slabs cross section we have taken. Okay, so this lateral shift we are going to calculate. I mean the value of O1m we are going to calculate. So this one we have taken I1. In the previous diagram, this one we have taken R1. This is also R1 and this is I2. I2 means equal to I1. Thickness is D. Refractive index is mu. Clear? So the expression for lateral shift is equal to O1m, that is perpendicular distance between these two directions. This O1m is called lateral shift. If this one R1, what about this angle? See, this one I1, we have proved this one I1. So its vertically opposite angle is going to be I1. Vertically opposite angle is going to be I1, isn't it? Just a minute. So we are going to find this O1m, which is lateral shift, and this lateral shift O1m, when we are going to find, we will find its value in the triangle O1m O2. In the triangle O1m O2, what is happening? Just check. O1 in triangle O1m O2. In this triangle, lateral shift O1m, that O1m will be O1 O2 sin I1 minus R1, isn't it? It's going to be sin just a minute. Not allowing to shift. And changing the board. Just after, let me finish it. Then I'll change the board. Because this one disturbs a lot. Okay, whatever. It is going to be O1, O2 as soon as I start. This is so nice board, but sometimes malfunctioning will be there. It is compulsory for this board. So I need to change. I go back to the old one. Just a minute. Please wait. Let me do. I'll do it by the same diagram only. There will be no change in it. Just a minute. Give me some time. We can do it here. Just let me remove this, otherwise again there will be problem. Same diagram you draw here. This will behave properly. So light ray entering. Just let me draw once more. Yes. So for that rectangular glass slab, I am drawing the same diagram here. Light ray enters this one I1 R1. It may be due to poor network connection also, no? Might happen with this. Otherwise, it can never happen. Network issue. It is troubling a lot. R1, this is R1, this is I1. This point we have taken O1, O2, this perpendicular we have dropped O1M. So lateral shift, we have seen O1M, which is nothing but O1 O2. This we have proved. This angle is I1 minus R1. O1 O2 sine of I1 minus R1. Okay. Now, if the thickness of the slab is T, this O1 O2 we can express in terms of thickness of the slab T. In this triangle, T divided by O1 O2 equal to this angle we have seen that R1. So T by O1 O2 will be cos R1. So the value of O1 O2 equal to T by cos R1. Just put it there. T by cos R1 sin I1 minus R1. Clear? Thickness of the slab is T. This is lateral shift. Light was going this way. After passing through the glass slab, it changes its path. Okay, as if it is shifted by the slab by some distance, which is equal to O1M. We are going to find its value. Now evaluate this. It is sin I1 cos R1 cos I1, this divided by cos R1. Isn't it? We can simplify it to get a better form. Lateral shift T into sin I1 sin R1 by cos R1. Clear? Go step by step. Little bit disturbance was there. Now you try to understand. So we got lateral shift, which is given by O1M. The value of O1M is O1 O2 sin I1 minus R1. Sin A minus B we expand, it is sin I1 cos R1 minus cos I1 sin R1, that divided by cos R1. Now separate, then it will be cos R1 getting cancelled like this. Okay. Now at this point, at O1, mu equal to what? Sin I1 by sin R1. Therefore, it is sin I1 by mu. Just substitute there. Sin I1 by mu, that divided by is that clear? Understood? So this is the value of lateral shift. We can get further simplified form. If you go on simplifying it, this LS or lateral shift, finally I am writing LS you take sin I1 common, T sin I1 common, 1 minus by under root is that clear? So this is the value of lateral shift produced by a glass slab. Any confusion? It's all right. Simple trigonometry. Keeping in one frame, try to understand, ask, doubt, anything you have. So this is the final expression for lateral shift. If it is given the length of slab, suppose I am going to solve a numerical, a problem. Rectangular glass slab has length equal to 2 meter. Light incident at an angle 30 degree. The slab has refractive index 1.5. Okay. Find LS. Lateral shift. Just put the value over there. That T will be replaced by L. So this is going to be equal to lateral shift LS T. T is what? L. 2 sin 30, 1 minus root 3 by 2 under root 1.5 whole square sin I1 sin 30 degree half, so it is 1 by 4. Just simplify it. This will be 1 minus, this is 3 by 2 whole square, 9 by 4. So it's coming something like this. 1 minus, you can easily find how much is the lateral shift from here. Root 6 value you substitute. Approximately 2.42, something like that. Okay. Understand? T sin I clear? Yes, sir. So lateral shift can be determined just by using this formula. Now we are going to deduce the relation when light passes through a spherical refracting surface. You try to understand a spherical refracting surface first. Spherical refracting surface. It is a part of sphere. Spherical mirror is part of the surface, but here it is going to be part of a glass sphere. I mean, it's like this. It is a surface, no? You can take this portion. Which one? This portion you can cut out. Suppose it is a part of large sphere. Then you got a refracting surface like this. This portion you take out from the glass sphere. Then it will look like this, which is a convex spherical refracting surface. Understand what I said? If you take that portion out, it looks like that. Okay, this is a spherical refracting surface, and this portion, if whatever medium is there, the same medium will come here, isn't it? Same medium will be there. This is a spherical refracting surface. Don't say that you will not bound it by using another curved surface, not required. It is a spherical refracting surface. And this will name as convex spherical refracting surface. This can be referred as convex spherical refracting surface. Why? As it is convex towards the rarer medium. That's why it is convex spherical refracting surface. From here only we can cut, or we can manufacture a surface like this also. Then that is called concave spherical refracting surface. This is concave spherical refracting surface. Okay? Through both the surfaces, or both are part of a sphere, so a geometric center can be taken here, and this is the pole. I mean, this is the midway. Just join. This is going to be the axis of the spherical refracting surface. Clear? And here center will lie here. Then you will be getting the principal axis. This is the midway between these 2 points A and B, taken here also. Here also. Okay, this is midway. We don't say it is pole. You say pole, no problem, but it is a spherical refracting surface. No? Midway between the two end parts is called the pole in case of spherical mirror. Here it is just the point midway between two. Now join these two. If you refer pole, okay, no problem, and center of curvature, you get the principal axis. This is the principal axis here. This is principal axis. On this spherical refracting surface, we are going to consider the refraction of light. Let us start with this convex spherical refracting surface. You will manufacture the refracting surfaces in such a manner that this face always will convex towards the rare medium or concave, no other way in between. So I have to find relation between object distance, image distance and a radius of curvature. This part going to be a radius of curvature. But where will you keep the object? How images are formed? That you have to know. So let us consider image formed by a convex spherical refracting surface. Image formed by a convex spherical refracting surface. Here also real image and virtual image, two different types of images can be there. So let me do it. This is your convex spherical refracting surface. Ray of light entering. What way entering? Ray of light entering. This has refractive index mu2. Surrounding has a refractive index mu1. Okay, this is center of curvature of the sphere C. When a ray of light enters from a point object, you take the point object here, ray of light incident here, so it get refracted. What way? This is normal. From object, light will go this manner to form the image. It is confirmed as if you sending light ray this manner, it will pass through, they will meet at the point. Okay, so that is going to be the position of image. Am I clear? From here, once more light ray incident. It suffer refraction. You give the arrow. Then what is happening? This point O, we have taken object, then this is going to be the image. Object, image. You need to find the distance between this object distance U. The image is formed here. Where? At I. So this is going to be V. This part U. This part U. Object distance U. This one is V. And radius of curvature is R. Okay. The radius of curvature is r. A is the point of incidence. A is the point of incidence. You can have a bigger diagram. If you like, you can have a bigger diagram. This diagram will be okay, or I do a bigger diagram? Bigger one. Doing it. Just doing it again. We are doing it for convex spherical refracting surface. Just a minute. This is your principal axis. This is spherical refracting surface. Object is there where on the principal axis you take any point, no issue. Can't say that I have to take at one position only. You take it here arbitrarily. Then send a light ray this manner. Then normal. Yesterday, last class I told you so many times. Then refracted ray going this way, getting refracted this way, and send another ray this manner. This is also meeting at which point? At this point only. So this is going to be the image, and this is center of curvature, this is normal. Okay, this part I showed you. This is going to be U, this is V, and this portion is R. So angle of incidence, this I, angle of refraction here, that is R. Okay, angle of incidence you take I, angle of refraction is equal to R. I, this is R. Mu is the refractive index here. This mu, if you take mu as the refractive index, then you consider refraction at O. At O, no, this point you take P. Consider refraction at P, this point. So mu is the refractive index, or you take this one as mu2. Outside is mu1. Mu2 here, inside, outside is mu1. So at P, mu1 into sin I will be equal to mu1 into sin I, not like this. Just find the, use the generalized Snell's law. Mu1 into sin I equal to mu2 into sin R. Clear? We have to relate U, V and R. So this is your I, this is R. Incident ray, suppose it makes an angle alpha. Imagine that the incident ray makes an angle alpha with principal axis. Refracted ray makes an angle beta. I am drawing the diagram, showing you the diagram. This angle you consider what? Incident ray with the principal axis. Let it be alpha. Refracted ray with the x-axis. This is beta and this one gamma. Clear? If you don't understand diffraction through spherical refracting surface, lenses also cannot be done. That's why I am taking time to explain. Prepare it with me only, so that you need not open any book at home. What I am going to relate? Relation among I, R, mu2, mu1. There are some points to note. Light rays will be allowed to fall from left side. Incident and refracted ray make small angles. Rays are paraxial, and those angles also small. Distance is measured from this point P. Let me take pole. Along the direction of light, everything positive. Opposite to it, negative. See the diagram here, what is happening? In this diagram, I equal to alpha plus gamma. You can see that. And gamma equal to this R plus beta. Am I correct? It's alright. I equal to alpha plus gamma. Why? Because exterior angle equal to sum of two interior opposite angles. That's why I equal to alpha plus gamma. And again exterior angle equal to sum of these two interior angles. So gamma equal to R plus beta. Now from 1, alpha beta can be written as tan alpha tan beta. Why? As alpha is small, so we replace alpha by tan alpha. But tan alpha is what in diagram? For that, this point of incidence you take A, because already P is in use. From A you draw a perpendicular. AL is the perpendicular. AL is the perpendicular. So tan alpha in the diagram you can see. This is nothing but AL by LO. It is AL by LO. Please write it properly. And tan gamma is what? Tan gamma. It is AL by LC. Okay? But now P and L are very close. P and L are very close. So all LO we can replace by PO. All LC by PC, that you write. now as P and L are very close, so I can written as AL by PO plus AL by PC. Clear? I will get this, you take number 3. Then what about the second relation? That also I have written that gamma equal to R plus beta. How can I write R here? Tan R? No, you write R equal to gamma minus beta. Tan gamma minus tan beta. Tan gamma is what? AL by LR. And tan beta is what? Check. Tan gamma. AL by LR. And tan beta is AL by LI. Where I is the image, O is the object. This is all right. So we got I, we got R. I we got here, R also we get here. After getting I and R, go by generalized Snell's law. At A, 1 into sin I equal to mu 2 into sin R. Clear? 1 into sin I equal to mu 2 into sin R. But I mean, if I and I small angles, so this we can replace by I and this by R. What is I? One by PO plus 1 by PC, and this is equal to mu 2 into R. AL by LI. Okay. This PO this AL we don't replace. Oh, we have taken AL common. Fine, fantastic. It's correct. 1 by PO. Now this AL is common in both the places. Cancel it out. What about PO in the diagram? You can check. PO is what? R. Along the direction of light, positive. PC is what? Achha, PO is what? PO. No, I have written wrong. PO means what? O is the object. So it will be P2O. This is going to be P2O. Isn't it? This thing going to be P2O. Yeah. Check. If you put the value of PO now. Put the value of PO now. Just see the diagram I have written over there. P2O distance is U. So we take 1 by minus U, opposite direction of light. PC how will I take? Along the direction of light. C is there. So this will be R. 1 by LR. 1 by R minus 1 by what? This is what? Li. 1 by V. Check it once. convex spherical refracting surface, PO negative, R is positive along the direction of light, L to R. How did I get LR? What is LR here? Check once. Tan gamma is what? Oh my god, AL by LC, extremely sorry. AL by L to C. And tan beta is what? AL by LI. LI is V. And LC is R. Check it for left side. AL into 1 by PO. PO is along the direction of light. It is AL by PO. Sorry, opposite direction of light, minus. And AL by PC. Check once. AL getting cancelled. 1 by PC. This is plus R. Have I done correctly? Or a negative sign not matching here in my calculation? A negative sign is not matching in my calculation. One plus minus problem I am getting. No, I got correct thing, I think. Only this one, this need to be positive. Check once how it is negative. Check. R is equal to tan gamma minus tan beta. Tan gamma is what?
alpha plus gamma ছিল
হ্যাঁ
তো আপনি তো এখানে মাইনাস করেছেন না এর 1 বাই পিও মাইনাস প্লাস 1 বাই পিসি হবে তো
oh yes, right. So this is correct. Now take this mu on left side or this R on right side. So the relation is this is the relation. Okay. So no more live class today because net is disturbed. I'm not happy